All right, we're going to talk about the overall game plan for how symmetry can help us understand the number of bands in an infrared spectrum. Okay, we're going to need a little bit of groundwork to understand this. So I'll start talking about a really simple system, the helium atom. So the helium atom um, has what's called 3 degrees of freedom. So if I had a container with just a single helium atom in it, the helium atom could move in the z direction, the x direction, and the y direction. So this atom has 3 degrees of freedom. Um, if we take now a 2 atom system like dihydrogen, so the hydrogen atoms that compose dihydrogen, each of those started out with 3 degrees of freedom. So before H2 was formed, this one had 3 degrees of freedom, and this one had 3 degrees of freedom. But now we've tied the two together, so we've limited the freedom of those atoms. And so now we would start out with 3 times 2 degrees of freedom for the 2 atoms. Now all of those, some of those movements get lost. So we have now translation of the whole molecule in the x, the y, and the z direction. So there's 3 translations of the molecule. And there's 2 different rotations that are good rotations for this molecule. So in this coordinate system that I have here, I could rotate about x or about z. So this one has 2 rotations and 1 vibration. So for the H2 molecule, I have 3 translations, 2 rotations, and 1 vibration for that molecule. We can use a formula to do this for us. For a linear system like H2, there are 3n minus 5 vibrations. For a nonlinear system like H2O, formula is slightly different, 3n minus 6. N here is 3, so 3 times 3 minus 6 means that there's 3 vibrations. So this has 3 translations, 3 rotations, and 3 vibrations, for a total of 9 again. So the individual atoms, when they were individual, this had 3 degrees of freedom, this one had 3, and this one had 3. So we don't lose any degrees of freedom in doing this process. They just become different things. So some of those movements, some of those translations that just the individual atoms had become rotations, some of them become vibrations. We're left with 9 at the end. So let's summarize our 2 formulas that we have here. 3n minus 5 for a linear molecule, and 3n minus 6 for a nonlinear molecule. So most molecules are nonlinear, so most of them will be 3n minus 6 vibrations. Okay, so that's the first step, is for us to figure out how many vibrations that a molecule will have, and all of those it will have for sure. But then the symmetry simplifies the whole process for us. So what the symmetry is going to do is, so we've got a molecule, and we figure out, let's say it's nonlinear, we figure out that it has 3n minus 6 vibrations. we can go through just using the symmetry of the molecule and figure out which of those vibrations are infrared active. To do this, we do what's called a normal mode analysis. This is one way of calling it. Also sometimes called a 3N analysis. And what we do is, if we want to use water here again, we actually go through and we think of setting a series of 3 vectors on each of the atoms. So 9 total vectors that we have here. We go through and we do an analysis. That analysis spits out the symmetries of the rotations plus the translations plus the vibrations. We'll go to a character table, and the character table will allow us to, out of this total, remove the rotations, remove the translations, and we're left with the symmetries of the vibrations. So this is the overall plan for what we do. Figure out how many total vibrations the molecule has, figure out the symmetries of all of its normal modes, including rotations and translations, subtract out the rotations and translations, and we're left with the symmetries of the vibrations. Okay, so for any of these molecules that we do, all 3n-6 vibrations are occurring. However, when we do this analysis, some of these vibrations will be invisible to infrared spectroscopy.